Video, the focus will be on simple and compound growth. This will be covered in lesson 1. Next, we will focus on applications of simple and compound growth. That will be done in lesson 2. And finally, in lesson 3, we will focus on foreign exchange rates. In lesson 1 of this video, the focus will be on simple and compound growth. We will start by considering specific outcomes for lesson 1. In this lesson, we will focus on important terminology linked to financial mathematics. After that, the meaning of simple interest. Then we will consider a formula for calculating simple interest. The next outcome will be simple interest calculations. After that, we will focus on the meaning of compound interest. Then we will consider a formula for calculating compound interest. And finally, we will consider a number of compound interest calculations. We will start by looking at important terminology linked to financial mathematics. A central concept is that of appreciation or growth, and this occurs when a value increases. This may be in a value of an investment or even an item for that matter. Two types of growth will be considered in this video, namely simple growth and compound growth. And together with that, a central concept is interest, normally denoted by I. Now, interest may be earned, and that is normally from an amount of money that is invested. So interest implies that we may add value to the initial investment amount, but interest may also be owed from an amount that was borrowed, for example. Interest rate, of course, is the expression of the amount of interest that is charged over a particular period. That normally is denoted by R, and it is in percentage form, a percentage rate for an investment or a percentage rate charged for an amount borrowed. Two ways to apply the interest rate then. It is important to note the relationship between the interest rate denoted by R, which will always be in percentage format, and I, which will be the same expression of the interest rate but now in decimal form. So we have to take the interest rate expressed as a percentage and divide by 100. Then we have the interest in decimal form. Now here is an example. Say we have the interest rate per period as 12%. Then clearly, correspondingly, the interest rate in decimal form will be 12 divided by 100, or 0.12. You can always express this as 0.12 as well, up to the accuracy as indicated. And that is an example of how we convert interest rate in percentage to just interest rate in decimal form. It's very important that you should be familiar with this just exchange in the format from percentage to decimal form. Now, capital P normally denotes the amount borrowed or invested, it doesn't matter, but it's referred to as the principal or the principal amount in the formula that will follow. Also, capital A normally denotes the final amount, or it is referred to as the accrued amount. If one invests the principal amount, initial amount, then obviously we earn interest over time, and together they will form the final or accrued amount. And this is then the notation that is used to indicate this particular amount right at the end, for example, of an investment period. Finally, very important to note that the small letter n denotes the number of investment or growth periods, and it expressed in some cases in years, other cases it may be a term or a quarter, and in some cases it may even be in months. So it's important to note the number of investment periods denoted by the parameter small n. in this particular context. We will now consider the question, what is simple interest or simple growth? Simple interest is a fixed percentage of the amount invested or borrowed and is calculated on the original amount. When simple interest is applied to an investment or a loan for that matter, the value of the investment or loan increases by an agreed fixed percentage at specific regular time intervals. Now, simple interest entails adding a constant amount. That's important. It distinguishes this from compound interest, a constant amount to the principal amount at regular intervals. So the constant amount to be added to the principal at regular intervals is equal to P times I. Recall the formula or the notation that was discussed in the previous slide. P is the principal or initial amount times the interest rate in decimal form. One can also have the formula in terms of the interest rate as a percentage R, but then you have to divide by 100. So this is then the constant amount to be added to the principal at regular intervals to constitute the simple interest growth in such a situation. Next, we will explain how to generate a formula to calculate simple growth. Let's assume that a principal amount P is invested or borrowed for n interest periods at an interest rate of I. Now, the accrued or final amount at different time intervals are as follows. After the first time interval or period where the interest apply, we have that the first accrued amount, the final amount at the end of the first interest period, will be the principal amount plus the interest earned, as was discussed on the previous slide. Now, if we take P as the common factor in this case, we have the accrued amount after the first interest period to be P times, in brackets, 1 plus I. Now let's have a look what will the accrued or final amount be after the second interest period. That is when n is equal to 2. So the second final amount after the second interest period will be, of course, the amount that applied at the start of the second interest period, namely A1 that we had before, plus another constant amount of interest that will be added. Now recall, simple interest implies a constant amount will be added after each interest period, and in this case, if you replace the A1 with the formula we had before, P times 1 plus I, and add another interest amount for that period of P times I, we can consolidate and write this as P common factor 1 plus I, or 1 plus 2I in brackets times P. And that will be the accrued amount after the second interest periods. And so we can continue and follow this argument through to where we finally, after n periods, will have that the final amount after n interest periods, where simple interest of course applies, will be P times, in brackets, 1 plus n times I. And that is the important formula to calculate simple growth. To summarize then, we have the simple growth formula as stated, which relates the final or accrued amount if a principal amount is invested for n interest periods at a simple interest rate in decimal form of I. Now the total interest earned over this particular period will be given by the formula capital I is equal to P, capital P times I times N. Now it's the principal amount times the interest rate in decimal form. That is the interest earned for each one of the n interest periods. And if we multiply together, we get the total interest that must be added to the initial or principal amount in order to find the final or accrued amount in such a simple growth situation. Let us have a look at a specific case where simple interest applies. And in this case, we would like to compare the accrued amount with the growth period for a particular type of investment. So assume that an amount of 100 Rand is invested or borrowed for a period of 10 years at a simple interest rate of I equal to 0.07. Now, of course, this agrees with the interest rate R equal to 7%. And let's make the interest period 1 year. So we have 10 interest periods to consider and a principal amount of 100 Rand. Of course, we can calculate after each interest period the accrued or final amount A sub n, like we showed in the previous slide, using the formula P times in brackets 1 plus I times n. And then we can find these accrued amounts A sub n at the different time intervals, which agrees with, of course, the years as indicated from year 0 to year 10. This can be done manually, or I can suggest that you actually use your Casio calculator in table mode to complete the set of ordered pairs, input, output. So we put in the value for the interest period, and out of there we would like to generate the final amount or accrued amount at the end of that particular interest period according to the given formula that we have discussed before. And of course, you have to complete this input-output table below using this particular formula. If we substitute the value that we have for P and for I and for N. Now notice that in this case we have replaced the N with an X and we have replaced the A sub N with a Y. We can see this as a function, a linear function, where the input will be, in this case, the interest period, the number of the interest period, and the output, of course, in this case would be the accrued or final amount at the end of that particular interest period. Now I suggest that you actually pause this video at this stage and complete this table as part of an exercise, just to get to feel what the simple interest growth means in terms of the accrued amount versus the growth period. But let's have a look at the final table then. Here we have the number of the interest period after 0 years right at the start. Clearly we have again our principal amount. Nothing has changed. So the final amount and the principal amount will agree, of course, at that point when n is equal to 0. After one interest period, we have calculated the interest that must be added to the 100 Rand, and that will be 7, of course, and it makes the final or accrued amount 107 Rand. And in the next interest period that will grow to 114, and so on. So it's very clear if you look at this table, the input-output table for the simple interest growth situation, that we have here a linear growth situation where as the time moves on and the interest periods increase, there is a constant amount of interest that was added to each of the accrued final amounts for that particular growth period that was considered. Let us now have a look at the graphical view of the simple interest example we have just considered. Here we have the input-output table for the interest periods from 0 to 10, and we saw that over each of the 10 interest periods over the 10 years, 7 Rand was added as a result of the simple interest that was earned over each period. Here we have a graphical representation of the situation. Right at the start, for the principal value of 100, we know that we at the start of the first interest period, that's where we have a 0 here. If we now represent growth, the number of growth periods on the x-axis or the horizontal axis, and on the vertical axis or the traditional y-axis we have the accrued amount, A sub n, represented. So these ordered pairs that we see from our table we can plot as points. We've seen a similar situation when we discussed the linear function before in a previous video, and we can see there is a linear growth of the final value or the accrued value over the 10-year period. And we see that the overall period is 10 years, delta n, change in the interest period. And then of course the total interest after 10 years, we can see the change from the initial value to the final accrued value is 70. This we can also see from our table, that the money has grown from 100 Rand, 7 Rand was added each year, and it ended finally at an amount of 170 Rand. Now this is a graphical view of the simple interest growth situation that was valid for the particular investment over a 10-year period. To summarize, let us then review the relevant parameters once more, having this particular graphical representation available at the same time. We know that the accrued amount or final amount for an investment where the simple interest applies is linked to the principal value and also the interest earned over the period as indicated, that we have saw in previous slides as well. But we can think of the representation of such a situation as we have on the screen as a linear function where of course the output value in this case represents the accrued amount, and the input value of course the number or the interest period, the number for the interest period. And of course in this situation we see that the value in brackets P times I represents the gradient in this case, okay, and C, the y-intercept, is represented by the principal amount. This is the way we can model the growth formula if you compare it to the linear function y is equal to mx plus c. In our case, the accrued value is a function of the input number which represents the interest period n. And of course, as I've showed you before, the y-intercept when n is equal to 0 just gives us the principal amount or the amount of money that was initially invested to start out the process. And as I've mentioned, the gradient is P times I, which in our case is then just 7. And note that the gradient is positive. That is why we have a growth situation in such a case where the simple interest applies. Next, we look at an example where we calculate simple interest earned. Let's have a look at this example. An amount of 1,050 Rand is invested at a simple interest rate of 4.75% per annum for a period only of 9 months. Calculate, first of all, the simple interest or the growth earned on the investment over this period, of course. And secondly, the final value of the investment, that is the accrued value after 9 months. Now, what we know in such a case, if we think of the formula that will apply in this situation, is that the principal amount is 1,050 Rand. We have that I is 4.75 divided by 100, that is the interest, in this case, in decimal form. Okay, that is per annum. And the number of interest periods in this case, we have only 9 months, and we have the interest period 1 year, or 12 months. So the interest period is not even one full period. So there we go, 9 over 12, which gives us 3/4 or 0.75 years. Notice that the number of interest periods may even be smaller than 1. In fact, it can have any positive real number value in this particular situation. So the amount of growth in this case over the 9 months period, or the interest earned, will be, as discussed earlier, the total interest will be P times small I times N, and we need to just substitute the values as shown in the green part of the screen from the information that was given, and we have an overall amount of 37 rand and 41 cents that constitute the total interest earned over the 9 months period. In the second part, the final value of the investment clearly will be the principal amount or initial amount, add to that the total interest. So in our case it's 1050 rand for the initial amount and 37 rand and 41 cents. Added to that gives us a total final value or accrued value after 9 months of 1087 rand and 41 cents. Note that alternatively we could have used our exponential growth, not exponential growth, our linear growth formula that we saw before for simple interest, that is A is equal to P in brackets times 1 plus NI or IN, it doesn't matter, and if we substitute the values we get exactly the same amount as before, namely 1087 rand and 41 cents. We next look at a second similar example of where simple interest applies. Here we have the problem. A lady invested 4,000 rand at 8.75% per annum in a fixed deposit account. If simple interest is paid at the end of 4 years, calculate first of all how much money she will receive, and secondly how much interest she will earn. Now let's just consolidate what we have available. So we write down everything that we know that may apply to this particular problem to enable us to solve it. Always a good idea to do that right at the start. So we know that P, the principal in this case, is 4,000. I is 0.0875, that is the interest in decimal form. We divide the given interest rate divided by 100 gives us I, and we know it's per annum, and interest will be paid over 4 years, so N is equal to 4 interest periods. So in the first instance it's straightforward. If we apply our growth formula for simple interest and substituting the values and calculating, making use of your calculator, we see that the investment will grow to 5,400 rand after 4 years. And in part 2, how much interest will she earn? Clearly we know from a previous statement about the relationship between the final accrued value and the initial investment or the principal. The total interest, capital I, is the difference between the two values, A and P, and in our case it will be 5,400 rand minus 4,000 rand, and it gives us a total amount of 1,400 rand that was generated through simple interest over the 4-year period. Or alternatively, one can just take the formula that we've seen before as well, the alternate way of doing this. Capital I is equal to the product of P and small I and N. In other words, we take 4,000, multiply with 0.0875 times the 4 interest periods, and you should get exactly the same value, 1,400 rand, as the total amount of simple interest that was earned over the 4-year period. In some cases, one wants to save to have a particular amount after some investment period, and in such a case we have to then calculate what principal value must be invested in order to attain that particular funding level as an accrued amount or final amount after such a period. Now this example is a case in question. How much money should you invest in a fixed deposit account paying 9% simple interest per annum if you would like to receive 8,000 rand at the end of 5 years? So can you see it's slightly different to the previous problems or examples? In this case we know what the final amount is. We know what the interest is. And we know the interest period, or the number of interest periods in this case. So we need to manipulate the formula that we have in order to actually calculate how much money should I invest to start out with to achieve this particular accrued value after 5 years. So the summary then, we have the accrued amount 8,000, I in our case again in decimal form 0.09, and n is 5. The unknown in this case is not a but p. So we start out by considering our growth formula for simple interest, and we rearrange to make p, the principal amount, the subject of the formula. And that you should be able to do. Divide through by 1 plus in brackets, rearrange, and we have the principal amount would be the accrued or final amount for the investment, and in this case it is something that I know, divided by 1 plus I times n. And substituting the values in this case and calculating, making use of your calculator again, we see that I have to invest 5,517 Rand and 24 cents in order to ensure that I have an accrued amount of 8,000 Rand after 5 years. I think you're ready now to tackle the first tutorial of this particular video, that is on simple interest, and it's linked to lesson number 1. Here we have the problems for the tutorial. The first problem: a student borrows 15,000 Rand for 3 years at a simple interest to pay for his studies. If he has to pay back 20,625 Rand at the end of the 3 years, what rate of simple interest per annum is he paying? Secondly, if I invest 15,000 Rand in a fixed deposit account at 10% per annum simple interest, how long will it take before I will have 45,000 Rand? Now think about these two problems. It all relates to the formula for simple interest, and you should be able now to manipulate and actually solve both of these problems on your own. So I suggest that you pause the video, do tutorial 1, and then come back and view possible solutions. Let us have a look at the suggested solution for problem 1 of tutorial 1. Here we have the problem once more, and let's start by summarizing the relevant information that will enable us to solve this problem. Always a good idea to have a good look at what you have available before you actually think of the strategy or the formula that may apply in order to solve the problem. In this problem we have the principal amount is 15,000 Rand, and we see that this amount has grown after 3 years to an accrued amount of 20,625 Rand. That is after 3 interest periods. And we're interested here to actually calculate the value of I, which interest was in effect here, simple interest in this case. So we need to be careful here. We start with our very basic growth formula for simple interest, but we have to make I the subject of the formula. So be careful to manipulate this carefully. Divide through by p both sides of the equation, and we have this equation as shown on the screen. And then of course it's just a matter of taking the term plus 1 to the right hand side and divide through by n to make I the subject of the formula. Now notice that this particular formula gives us a compound fraction, and the video series, one of the first videos on basic algebra, deals with compound fractions and how to simplify them. So go and have a look and see if you agree that this can be written as shown on the screen, namely a minus p, the accrued amount, minus the principal amount, divided by n times the principal amount. That is the formula then for I that I need in order to solve this problem. Now I substitute the values for this particular formula, and we get in this case the I value to be 0.125, or if we think of this as a percentage, it's 12.5% interest per annum that was paid by the student who borrowed the 15,000 for 3 years. Note that you can also use this particular simplified version for the formula for this compound fraction, which represents I, and you should get exactly the same value in this case. And finally then we can say without doubt that a simple interest rate R of 12.5% was paid in this particular case. In problem 2, I invested 15,000 in a fixed deposit account at 10% per annum, simple interest. How long will it take before I will have 45,000 Rand as the final accrued amount for this investment? As I suggested before, let's make a summary of what we have available in what is actually required to calculate in this particular case. We have the principal amount, 15,000. We want the accrued amount to be 45,000, and we're interested to find out how long will it take for that to happen, if of course the I value, that is a simple interest in decimal form, is 0.1. So we start with our formula, which links these parameters together, the simple interest growth formula, and we need to make in this case clearly n the subject of the formula. That is what we have to calculate, the number of interest periods. How long will it take before the initial amount of 15,000 will become the final amount of 45,000 Rand in such a case? So the first step will be to divide through by P both sides of the equation. And then of course we isolate I times N as the subject of the formula by writing the +1 on the left as -1 on the right hand side. We make this one fraction with the common denominator P. You should all know how to do this. So we have that I times N is equal to A minus P divided by P, which of course will mean that N is A minus P in the numerator position divided by P times I, or IP, in the denominator position as indicated. Now we're ready to substitute the values for A, P and I as indicated, and it seems that in this case, if you've done your calculation correctly, the period it will take for the 15,000 to grow to 45,000 will be 20 years. We will now consider a very important question. What is compound interest or compound growth? Simple interest for each period is always calculated on the original amount borrowed or invested before it is added to the accrued amount at the start of that period. When calculating compound interest, the interest charged or earned in each interest period applies to the accrued amount at the start of that period. This means that the principal increases or grows over the interest periods. Interest earned or charged for the next period is calculated on the increased principal amount at the start of each period. We will now show how one can generate a formula to calculate growth as a result of compound interest. Let's assume that an amount P, principal amount P, is invested or borrowed for n interest periods at a rate of I, in decimal form of course. Then this will represent the growth of that principal amount P over n interest periods, where n assumes the value 1, 2, 3 and so on. So let's see how this amount will grow if interest is calculated in this particular way, compound interest that is. In the first interest period, at the end of that period, we will have the first accrued amount, A sub 1, to be the principal amount plus the interest earned over that first interest period, which is P times I. So there's no difference between simple interest and compound interest in the first interest period. So here we have the amount P times 1 plus I, if we take P as a common factor. And now obviously this is the new accrued amount that will apply if interest is calculated in the second interest period. And this is what is shown in the next line. So the second accrued amount, that is after the second interest period, the original amount would have grown to A sub 2, being the accrued amount after the first interest period plus, now the new interest that we earn in the second interest period will be, of course, A1 times I. Remember, if you recall, in the case of simple interest, this would again be P times I. That is where the difference comes in. So if we take the formula for A1 that we have from the first interest period, P times 1 plus I, and substitute, then we see that we generate a common factor as indicated on the screen. The common factor is P times 1 plus I in this case. And if we take this, we're left with 1 plus I, and together with the 1 plus I, we have the accrued amount after the second interest period to be P times 1 plus I all squared. And exactly the same, if you repeat the whole process, just remember to use the accrued amount after the second interest period if you apply the formula. Then we see after the third interest period, we have the principal at the start of that third interest period, which is the accrued amount after the second interest period, plus again the interest generated in that period will be I times A sub 2. So we do not use P at all, we always use the accrued amount from the previous interest period as the amount with respect to which we generate or calculate the interest for a particular period. If we substitute the value or the formula P times 1 plus I squared in the place of A2, we see that we generate another common factor. In this case, P times 1 plus I all squared is a common factor, and the 1 plus I again gives us that 1 plus I raise its exponent by 1 from a 2 to a 3 as indicated on the screen. And again, we can continue this pattern exactly the same. You see the common factor P into 1 plus I cubed for the fourth interest period will result, after factorization, the formula to grow to P times 1 plus I to the power 4 for the accrued amount after the fourth interest period, and so on. So clearly at the end of the investment period, say the investment period was in interest periods as indicated in general, then we have the accrued amount after n interest periods if compound interest applies to be P times 1 plus I to the power n. So hopefully you'll have a good idea now where this compound interest formula comes from for growth of an initial investment P. To summarize then, the compound growth formula is given by the accrued amount after n interest periods will be the principal amount multiplied by 1 plus I to the power n, of course, where I is the rate for every interest period. As a first exercise linked to compound interest, we look at the accrued amount versus the growth period and have a look and see if you can identify a trend in this regard. Let's assume that a principal amount of P, let's make it 100 Rand, is invested or borrowed for a period of 10 years. So n is equal to 10 at a compound rate of I equal to 0.15. Of course, that corresponds to R being 15% per annum. We have from the formula on the previous screen the link between the accrued amount after the nth interest period and the principal amount and the interest rate as indicated, this formula that we have developed. So use this particular formula to find the accrued amounts A sub n at different time intervals n. So we start with a table, n equal to 0. That is, of course, the point where we start. That means we have the principal amount in that case, and then the interest period 1, 2, 3 up to 10 in this case, and correspondingly the output values in this case would be the accrued amounts according to the formula. So I suggest that you use your Casio calculator in table mode to complete this particular table, input-output table, according to the formula. And let's see what we've done here. For the inputs, we used the variable x, and for the output, the variable y. Although we're only interested in specific values for x and y, this is the formula that applies. And if you notice, this is really typically an exponential function. And we'll say more about that in a moment. But at this point, I suggest that you pause this video and complete this table or a similar table for a number of input values, and then come back and have a look to see if you can identify a trend. Here we have the completed table. N ranges from 0 to 10, and the output values correspondingly, A sub n, the accrued amounts after the nth interest period, in this case ranges from 100 to 404.56. Just check that you agree with the output values according to the particular value for the interest period. Have a good look and also see and check with your own table if you agree that the ratio between successive terms of the output values, in this case A sub n, will be constant, and the constant value in this case is 1.15. Now clearly this value agrees or correlates really with the interest rate that we have applied, 0.15, and if you take 1.15 and you subtract the interest rate, of course you must get 1. So in this case really it says that the growth pattern is exponential. Remember, if we have a number sequence, in this case A sub n, and the ratio between successive terms is constant, then we deal with exponential growth. So the growth as a result of compound interest then will be exponential growth. It is important to also consider the graphical view of compound interest. We use exactly the same example as before. We invest 100 Rand over 10 years, the compound rate of I equal to 0.15, and we consider the input-output table as we had it on the previous screen. Now we can decide, as we normally do with all functions, from the discrete to the analytical case, to plot the points, input-output values or ordered pairs as points on the Cartesian plane to get a sense, that is a visual sense or a graphical view of the growth as a result of compound interest. And this we can do, and there we have done it. We plotted the corresponding points from our table as indicated, and we have applied the best fit curve to get a sense of the growth trend for compound interest over a 10-year period if we invest 100 Rand to start out with. So let's just summarize then. We have had this formula which gives us the accrued amount or the output value for every interest period n as an input value, and we can really model this particular equation using our functional notation as y is equal to a times b to the power x, where a and b assume specific values. Remember, this is our classical exponential function. So we can view the output values or the accrued amounts after each interest period as a function of the number of interest periods as indicated on the screen, where of course in our case the value a, parameter a for this exponential function, will be the principal amount, and the value b will be 1 plus I, 1 plus the interest rate in decimal form. In our case it is 1.15. Now notice that this value is greater than 1, and this is exactly why we have growth. If this particular value lied between 0 and 1, for example, we will not have exponential growth, we will have exponential decay. So also the ratio between successive terms from the output values, you can look at this table again, was constant, and this is typically when we have an exponential function at work, but in particular in this case we will have an exponential growth function since the value is greater than 1. We will end off this discussion by looking at a comparison between compound and simple interest. Let's use exactly the same example as before, where we invest 100 Rand, the principal P, over a period of 10 years, and the interest rate then, in this case, 15% per annum as indicated. We'd like to compare compound and simple interest in this particular case. We can start by drawing a table as we did before, and we look at the number of interest periods, N, and correspondingly calculate the output values, the accrued amounts that correspond to those interest periods at the end of each of those interest periods as indicated for compound and for simple. And that's another exercise that you can try and do on your own. After this, we can plot this on the Cartesian plane as we did before and then compare. Graphically, if we do that, we see that the growth as a result of simple interest, the red graph, will be linear growth as we've discussed before, and as a result of the compound interest, the blue graph, we will have exponential growth. Comparing the two graphs, it is clear, once we have the best fit curve in both cases, that the interest will be the same, or the growth will be the same for the first interest period. I've mentioned that before. But in general, the compound growth is bigger than the simple growth if the number of interest periods is greater than 1. So it's much better, you get better return on investment, for example, if compound interest applies compared to a simple interest applies. But obviously if you borrow, then the opposite is true. So you will pay more in the end if interest is compound compared to simple interest in such a case. Let us consider an example of a typical real-life situation where we calculate accrued compound growth. A lady deposits 5,000 Rand in a fixed account for 7 years at an interest rate of 9.25% compounded annually. What amount of money will be available after 7 years? Now, as before, it's important to summarize all the relevant information that may apply to the solution for a given problem. In this case, we have that the principal amount P is 5,000 Rand. I, in decimal form, will be 0.0925, and N will be 7. So we have 7 interest periods of 1 year each. What is outstanding and what we actually would like to calculate is the accrued amount A. So clearly, if you use your calculator, you can compute this using the formula as we had it before, namely A is equal to P times 1 plus I to the power N. Just substituting the values in the right positions for P and for I and for N, we calculate and we have that the amount available after 7 years will be 9,287 Rand and 96 cents. In a second example, we consider calculating the compound interest given a problem where an initial amount or a principal amount must grow to a specific amount after a fixed interest period. Here we have the problem. What is the annual compound interest rate being charged by Africa Bank on a loan of 25,000 Rand if 45,000 Rand is to be repaid in 8 years' time in full settlement of the loan? And let's just agree that the interest rate in this case is per year, annually. So let's have a look. First of all, as normally is the case, we need to summarize the relevant information that is available and identify that which we would like to calculate. In this case, clearly we're looking for the interest rate I in decimal form per annum, and we have available the principal amount, 25,000 Rand, the accrued amount after the 8 years period, 45,000 Rand, and of course we have to apply the original formula again. But in this case we must make the interest rate I the subject of the formula. In other words, you have to manipulate this equation or this formula using some algebra and make sure that I is alone on the left hand side of the equation. That is the subject of this equation. So the first thing to do is to divide through both sides of the equation by the principal amount p to get a divided by p, and then take the nth root both sides of the equation, that is the inverse relation compared to the exponentiation by n, to get rid of it, in other words to get 1 plus I, and on the right hand side of course the nth root must still apply to the quotient a divided by p. And of course we send finally plus 1 to the right hand side to become minus 1, and now we have I as the subject of the formula, and we have the values for the parameters on the right hand side of the equation, and you can use your calculator in this instance to calculate the value of I by substituting the correct values for the parameters as it appears in this particular formula for I. If you do this, we get the final value for I to be 0.07623,983 and so on. So we need to decide here on the degree of accuracy, and if we decide on 3 decimal places, we can rewrite this value for I as R to be more or less, that is the interest rate as a percentage, 7.624% per annum. And that will then solve this particular problem. I think you will be ready now to tackle a tutorial on compound interest. So in tutorial 2 we have 2 problems. In the first one, an amount of 3,000 Rand is invested at an interest rate of 12% compounded annually. How long will it take to the nearest month, that is, to reach a value of 8,500 Rand? In the second problem, we would like to know how much money should you invest in a fixed deposit account paying 9% per annum compound interest if you would like to receive 8,000 Rand at the end of 5 years. I suggest that you pause the video, do this tutorial, and then come back and view possible solutions. Let us have a look at the suggested solution for problem 1 of tutorial 2. Here we have a problem where an amount of 3,000 Rand is invested at an interest rate of 12% compounded annually, and we would like to know approximately how long will it take to the nearest month, and that is important because that tells us the degree of accuracy that is needed for the final answer to reach a value of 8,500 Rand. Now let's have a look at the normal interest formula that applies in the case of compound interest, and let's see what is given and what we have to calculate. So clearly in this case, if we make that summary of the given information, we have the principal amount, the accrued amount, and the interest rate, and we're interested to find the value of n, the number of interest periods where the accrued amount will be 8,500 Rand, given that we start with 3,000 Rand as the initial amount. So clearly this formula here needs to be rewritten or reformulated to make the n the subject of the formula. But the first step in this case would be to write 1 plus I to the power n in terms of the accrued amount, final accrued amount, and the principal value as indicated on the screen. So substituting the values, in this case we have this equation. So really we need to find the value for n which will satisfy this particular exponential equation. Note that if we take 8,500 and divide it by 3,000, we have 2.83, and it's a repeating decimal. That is what this particular symbol stands for. So 2.8333, and it continues that way. So to approach this problem, just by experimenting with certain n values or the number of interest periods which will satisfy this particular equation, we can actually utilize our calculator very effectively to do an investigation to see possibly between which values will the actual answer lie, the exact answer which will satisfy this particular equation which we got from our compound interest formula in this particular format. So I suggest that you use the table mode of your Casio calculator, or an equivalent calculator for that matter, to determine the approximate values of n which will be such that this particular equation is satisfied. So let's look at our first attempt. If you, for example, and you can check this with me on your own, look at the interest periods, or the number of years in this case, 6, 7, 8, 9 and 10, and corresponding to that as output values, calculate 1.12 to the power n. Of course, this corresponds with our expression here. Then we see that in the first instance, if we use n equal to 6, the output will be 1.97, which is less than 2.833 repeating. So clearly n equal to 6 or 6 years will not be enough for the investment to grow from 3,000 Rand to 8,500. The same will happen if you choose n equal to 7, 8 or 9. But if you choose n equal to 10, we see that the output in this case will be 3.11, which is more than what we will be looking for to satisfy this particular equation. So less than 9 years will be an underestimation for the growth period, and 10 years or more seems to be an overestimation of the growth period that is necessary for this investment to grow to the desired value. So somewhere between 9 and 10 we have the correct answer, or the correct value for n, the number of interest periods for this investment to grow to exactly the correct amount in this case. So we have to give our answer to the nearest month, so we'll need to investigate a bit finer, or have a closer look, and look at values for n between 9 and 10 to see if we can get closer to the actual answer. Here we have broken up the values for n from 9 to 9.4, because we know somewhere between 9 and 9.4 as input value we will have the desired output value of 2.833. It seems to me it will actually lie between 9.1 and 9.2 years. If we use that particular, look in that range, we will find the correct value for n. And we can even break it up further, as we've done, and you can check this with your calculator, to have our output value to 3 decimal place accuracy, and we've broken up the input values to 2 decimal place accuracy. In this case, starting with 9.12 and ending with 9.2. We know it lies between 9.1 and 9.2, but looking at the output values, it is clear that the answer will actually lie to a 2 decimal place accuracy between the values n equal to 9.18 and 9.2. Because the output values, can you see, the first one is less than 2.833 repeating, and the other one is more than 2.833 repeating, 2.837, as you can see from the value table on the screen. Now we can actually continue and even refine our search to a 3 decimal place accuracy for the input values n in such an instance. And we end up finally with the approximation for the number of interest periods n to be 9.189 years if we continue, because that will be enough. If you translate this to months, the 189 of a year, we see that it really translates to approximately 9 years and 2 months that is necessary for this particular investment of 3,000 Rand to grow to an amount of 8,500 Rand. And this would be good enough as an answer in this particular case. In problem 2 of tutorial 2, we have to answer the question, how much money should you invest in a fixed deposit account paying 8% per annum compound interest if you would like to receive 8,000 Rand at the end of 5 years? Now it's clear that in this case this straightforward compound interest formula would apply. However, you will have to rearrange this formula, since we have in this case available the accrued amount, 8,000 Rand, the period of the investment, n is equal to 5 years, and of course the interest rate per annum, I is equal to 0.09 from our given interest rate per annum. We have to find the principal amount in this case. So rearranging, making P the subject of the formula, and substituting the values for a, n and I, use your calculator once more and see that you calculate the amount in this case for the principal amount to be invested in order to grow to 8,000 Rand after 5 years to be equal to approximately 5,199 Rand and 45 cents. In lesson 2 of this video, we will focus our attention on applications of simple and compound growth. Let us look at the outcomes for lesson 2. In this lesson, we will apply simple and compound growth to first of all hire purchase, secondly inflation, and finally population growth. To start this lesson, we consider the question, what is hire purchase? A hire purchase agreement is a financial arrangement between a buyer and a seller about how the buyer will pay for the desired product. Most loan agreements require that a deposit be paid before the customer can take ownership of the product. Principal amount of a loan is therefore the cash price minus the deposit. The accrued amount of the loan is then divided into monthly payments over a period of the loan. Interest on hire purchase or a loan is charged at a simple interest rate on the amount owing. Customer basically hire the item from, say, a shop. If the customer stops paying at any stage, the item can be repossessed or taken back by the shop. You are only the owner of the item once the last payment was made. Due to the risk factors, the seller sometimes adds an insurance premium to the monthly installments. Let us have a look at our first example where we have a hire purchase with a deposit. John decided to purchase a bicycle advertised for 2,700 Rand in the newspaper. The hire purchase agreement requires a deposit of 10% and that the loan on which the interest is charged at 8.5% per annum be settled by making 24 equal monthly payments. Calculate what John's monthly payments will be. Now let's summarize the information that applies in this particular case. First of all, it's important to note that a deposit of 10% of the amount, total amount, or the purchase price of the bicycle, 2,700 Rand, must be paid. Now, of course, this amounts to 270 Rand for this particular deposit. The principal amount of the loan will be the cash price, that is 2,700 Rand, minus the deposit that will be paid before this particular loan agreement takes effect. So, in this case, if we subtract 270 Rand from 2,700, we're left with 2,430 Rand. Now that is our principal amount in the case of the loan. The interest that applies is 8.5% per annum. In decimal form, I will then be 0.085. And since the interest is per annum, the interest period is over a year, and the payments should be made over a period of 24 months, we know that in this case the number of interest periods will be 24 divided by 12, or 2 years. So with this in hand, we're now ready to tackle this problem, to solve it. First of all, let's calculate the accrued amount of this particular loan over the period of 2 years. Remember, simple interest applies, so we have the simple interest formula that apply in this case. We only have 2 interest periods, 2 years, and this is the interest that apply per interest period. So in total, from the side of the loan that is made in this case, an amount, total amount of 2,843 Rand $2,810 is owed over this 2-year period, at the end of this 2-year period. Now clearly we have to pay this amount in 24 equal installments. So the monthly payments will then be this particular amount, $2,843.10 divided by 24, which gives us, and we have to make some adjustment here to round up or down in this case. In fact, if we round down to the nearest cent, for example, there will be a couple of cents outstanding or unaccounted for over the particular loan period, which one can actually add to any one of the particular installments in full settlement of this particular loan. Why is that? Well, let's have a look and see, because if we take this 118 Rand and 46 cents times 24 and you subtract that from what is owed over the loan period, then we're left with 6 cents in this particular case, and this can be paid or added to any one of the 24 payments to settle this particular loan in full. In the second example, we'll consider hire purchase plus insurance. Mary buys a TV on a hire purchase agreement. The cash price is 8,750 Rand, and interest of 16.25% per annum will be charged over the 42 months repayment period. An insurance premium of 13 Rand and 75 cents is added to every monthly payment. Calculate what Mary's monthly payments will be. Let's see what we have available in this particular case. Clearly the principal amount in this case will be the cash price, which is 8,750. The interest in decimal form will be 0.1625, and in this case the interest is per annum and the repayment period is 42 months, so N, the number of interest periods, will be 42 divided by 12 years in this case. Note that this is not necessarily an integer, so it may even be a part of an interest period that applies in terms of the repayment period as such. Now, we have that the accrued amount for this particular loan or hire purchase is given by our simple interest formula that we have seen before, and we have to just substitute the values for I, N and P as indicated, and then calculate this amount. This amount, of course, must be divided by 42 to find the installment per month, or the payment per month that must apply in this case in order to settle the particular loan amount overall. But be careful, we have to add 13 Rand and 75 cents to each and every one of these installments because of the insurance premium that must be added to our monthly payment. So this particular formula apply, get the total accrued amount divided by 42 plus 13 Rand and 75 cents, and that gives us an amount of 340 Rand and 57 cents for the monthly payment that is required in this particular case. Next, we consider a tutorial problem on hire purchase. The problem in tutorial 3 is as follows. Your father wants to buy a fridge on a hire purchase agreement. The cash price of the fridge is 7,500 Rand. He is required to pay a deposit of 17.5% and pay the balance of the loan off over a period of 39 months at an interest rate of 13.5% per annum. First of all, what is the principal amount? Secondly, what is the accumulated loan amount? Thirdly, what are the monthly repayments? And finally, what is the total amount he has paid for the fridge? At this point in time, I suggest that you pause the video, do tutorial 3, and then come back and view the solution. Let us have a look at the solution for tutorial 3. Here we have the problem once more. In this case, the father wants to buy a fridge on a hire purchase agreement, and the cash price of the fridge is 7,500 Rand. He is required to pay a deposit of 17.5% and pay the balance of the loan off over a period of 39 months at an interest rate of 13.5% per annum. Here we have a summary of the pertinent information, and see if you agree. The cash price, of course, 7,500. The deposit, 17.5% interest rate that applies in this case is in decimal form 0.135, and 39 months translates to n equal to 39 over 12 years, or interest periods in this particular case. So first of all, we have to find the principal amount. In this case, with such a loan agreement where the deposit is payable, it's the cash price minus the deposit. So it's 7,500 Rand minus 0.175 times 7,500. This represents the deposit, 17.5% of 7,500, and this gives us, of course, an amount of 1,312 Rand and 50 cents to be subtracted from 7,500, 6,187 Rand and 50 cents. In part 2, we have to now calculate the accumulated loan amount. So this amount A will be given by the principal amount that we have just calculated, multiplied by 1 plus the interest rate times, of course, the number of interest periods. Simple interest growth formula that applies in this case, and if you substitute the values as indicated, you should get, with your calculator of course, the amount of 8,902 Rand and 27 cents. That will be the accumulated loan amount. In part 3, we were asked to find the monthly payments. Now clearly the monthly payments will be the accrued or accumulated loan amount divided by the number of months over which this loan must be paid off, and it is specified as 39. So dividing that by 39, we get an amount of 228 Rand and 26 cents. In the final part of tutorial 3, we were asked to actually give the total amount that was paid back in this case. So the total paid over the period, the loan period, will be the deposit plus, of course, the accumulated amount, loan amount that is. So if you add the two values for the deposit, 1,312 Rand and 50 cents as we've calculated it, as well as the accumulated amount, 8,902 Rand and 27 cents, add that together, the total amount that was paid, in this case including the deposit, was 10,214 Rand and 77 cents. Make sure that your calculations agree with this. We will now turn our attention to the concept inflation. There are many factors that influence the change in the price of an item. One of them is inflation. Inflation is the average increase in the price of goods each year and is given as a percentage. Since the rate of inflation increases from year to year, it is calculated using the formula for compound interest. Also, a low annual inflation rate normally is an indication of a very healthy economy. Next, we will demonstrate the effect of inflation by calculating the future price of a well-known item based on inflation. The average inflation rate for the next 10-year period, based on statistical evidence, is estimated at 8.75%. A loaf of bread currently costs 7 Rand 56 cents. How much will it cost in 10 years' time based on the estimated inflation rate? So here we have the summary of the given information. In this case, our principal amount, P, will be 7.56. The interest rate that applies in this case, the average over the 10 years, average per year that is, I equal to 0.0875, and we're looking at a 10-year period, so N is equal to 10 interest periods, and we would like to know what is the accrued amount or the final amount after growth over this particular period as indicated. Now, of course, as I've mentioned, inflation links with compound interest per year, so we use the compound growth formula for this particular problem to calculate the accrued value after a 10-year period of the bread price, which initially, as a principal amount, starts at R7.56. The interest which applies and the number of interest periods 10, if you substitute that, we can actually calculate using this exponential growth formula linked to the compound interest to find the estimated bread price in 10 years time. So the estimation is that a loaf of bread will cost R17.49 in 10 years time. That is based on average inflation. In tutorial 4, we consider a problem on inflation. The current average price of a small car is 95,000 Rand. The average rate of inflation, based on statistical data, over the past 30 years was 10.65% per annum. How much did a similar car cost 30 years ago? At this point in time, I suggest that you pause the video, do tutorial 4, and then come back and view the solution. Let us consider the solution for tutorial 4. Here we have the problem once again. In this case, we're looking at a growth period over 30 years, and it started 30 years ago. So the price of a small car right now is 95,000 Rand. So this then represents the accrued amount, 95,000, and we have the interest, average interest, that's obviously inflation over the past 30 years as 10.65%, which translates to I equal to 0.1065 in this case. 30-year period means N is equal to 30, and we're really interested in the principal amount. What did a car cost 30 years ago? And of course it has grown, or there's a growth over 30 years to the amount of 95,000 Rand as indicated. So clearly our compound interest growth formula applies, but we're interested here in the principal amount to calculate that, so we make that the subject of the formula as we have seen earlier in some examples, and it's just a matter of substituting the values for A, I and N to calculate the cost 30 years ago, the average cost of a similar car in this particular case. So if we calculate, simplify, we see that the price of a similar car 30 years ago was 4,562 Rand and 27 cents. Can you believe this? Well, maybe you should ask your grandparents about that. The final concept that we will focus on in this lesson is population growth. Family trees grow exponentially as every person born has the ability to start another family of his or her own. For this reason, we can also calculate or model population growth using the compound interest formula. Population growth depends on a variety of factors. Growth of this kind is normally much lower in developed countries. We will now demonstrate how the exponential growth formula can be applied to calculate future population based on growth rate. The current population in Port Elizabeth is 1,786,630. The average population growth rate in PE, based on statistical evidence, is estimated at 3.16% per annum over the next 15 years. What can the city planners expect the population of Port Elizabeth to be in 15 years' time? So in this situation, we have the principal amount or the principal number as 1,786,630. The interest in this case corresponds to the growth rate for this particular applied problem. So I has a value of 0.0316 from the 3.16% growth per annum, and we have, of course, n is equal to 15 years. That is the number of growth periods, and we're interested in the accrued or the growth, total growth over this particular period that can be expected. So we use the exponential growth formula as before, substituting the values for p, I and n as discussed. We have that the population of Port Elizabeth is expected to grow to 2,849,080 in 15 years' time. So clearly the city planners must make provision for housing and basic service delivery for an additional, in this case, 1,062,450 people, which is a huge responsibility. In tutorial 5, we consider a problem on population inflation or population growth. A small town in the Eastern Cape province is experiencing a huge increase in births. According to the available statistics, the average growth rate for the next 5 years is estimated at 12.65% per annum. How many babies will be born to the current 2,450 residents in each of the next 2 years? Think about this problem. I suggest that you pause the video, do tutorial 5 and then come back and look at the solution. Let us have a look at the solution for tutorial 5. Here we have the problem once again. So in a small town in the Eastern Cape province, we have this particular situation, a huge increase in births. So initially the population is 2,450 and there is a growth rate of 12.65%. That's estimated per annum. And we have to find out how many babies were born firstly in the first year in this situation. So we have P is equal to 2,450, the initial number of people. The growth rate in decimal form, I is equal to 0.1265. And for the first year we can apply this formula where n is equal to 1. And we have after 1 year 2,759.9 people in the town after year 1. And clearly we must discard the 0.9. We cannot have 0.9 of a person, whether it's a baby or otherwise. So we settle then on 2,759 people at the end of year 1. That means that the number of newborns in year 1 totals the difference between the initial number of people, 2,450, and the number of people estimated at the end of that year, 2,759, which gives us the number of newborns in this case to be 309 for year 1. For the 2-year period, in this case over a 2-year period, that is when n is equal to 2, we can calculate the number of the estimated number of people after 2 years as indicated just using our growth formula, substituting the values, and we get in this case 3,109 people. Now in this case the newborns in the first 2 years will be 3,109 minus the initial population, which gives us 659 babies that were born over the first 2 years. In year 2, of course, we must still subtract the number of babies that we have estimated were born in year number 1. So 659 minus the number of babies born in year 1 gives us the estimated number of babies born in year 2 of this particular growth period. So that then settles the answer for tutorial 5. In lesson 3 of this video, we will focus our attention on exchange rates. Let us look at the outcomes for lesson 3. In this lesson, we will focus specifically on the meaning of currency and exchange rates, different types of currencies around the world, exchange rate tables, and finally conversion between different currencies. We will start this lesson by considering the meaning of currency and exchange rates. Different countries have their own currencies or monetary units. Currency is the type of money that a country uses to buy and sell goods and services. Exchange rates refer to the cost of buying currencies from different countries around the world. Exchange rates are important because countries trade with each other. For example, in South Africa, we import computers from America, for example, and pay them in dollars. On the other hand, South Africa exports apples to Europe, and they pay us in rands. So, exchange rates are important for individuals too. In some cases, they travel to foreign countries and will need the currency of that country to pay for local items. Let us have a look at examples of currencies of some well-known countries or regions. Our own currency in South Africa is called the Rand, indicated by capital R. And here we have an example of a 10 Rand note. The currency of the United States of America is the dollar. And note the symbol for the dollar as we know it also from our keyboard on the computer. Here is an example of a $1 note from the United States of America. The currency of the United Kingdom is the pound, and note the symbol that is used to indicate pounds. Here we have an example of a 20-pound note. The currency that is used in Europe is the euro. Note the symbol that is used to indicate the euro. Here we have some examples of denominations of the euro, coins and bills. The currency of Japan is the Japanese yen. Also note the symbol for this particular currency. And here we have an example of the Japanese yen. For more examples of currencies around the world, consult your local newspaper, in particular the financial section, or any financial magazine. We will now consider specific cases of exchange rate. Now, exchange rate deals with the comparison of the values of different currencies. Let us have a look and consider the table below. You can also consult your daily newspapers for the latest exchange rates. Now, if we want to compare, for example, the Rand, South African Rand, with some other currencies, then normally we have to note how many Rands will buy 1 unit of the other currencies. So it's a ratio between the value of the Rand and, for example, the other currencies listed in this table, the British Pound, the Euro, the US dollar and the Japanese yen. So for example, the exchange rate in Rand, okay, for the British Pound in this case will be 13.1702. What is the meaning of that? Well, the meaning of that is that we have to pay 13.1702 Rand to buy 1 pound. So it's the expression of the value of 1 unit of the foreign currency, in this case the pound, in rands, expressed in rands. So that is one way that one can consider an exchange rate. Hence the ratio of the value of the pound to that of the rand will be 13.1702 to 1. Of course, we can express the ratio in reverse order and ask the question, if I have 1 rand, how many pounds can I actually buy? Clearly this will be the reciprocal of the ratio that we have had before. And that we'll consider in the next slide. But in this table, for example, we see that 10.609 rands will buy 1 euro. So that is the buying power of the euro expressed in rand terms. Also the US dollar, 8.3555 that rands will buy 1 US dollar. And 1 Japanese yen in this case will cost you, in our case, 0.1076 rand. So that is just expressing the values of the foreign currencies in this case, as listed, the 4 in rand terms. Now, it is clear from this table that one can actually compare the strength of the currencies in pairs. So if we fixed the rand in the one case and the other currencies as listed in the table, we can really see that the first 3 currencies are stronger than the rand. It has more value. In the first instance, the pound, for example, has 13.1702 times the value of the rand in this particular table. And the yen in this case is a case where a currency is weaker than the rand. So I have to pay less than 1 rand for 1 Japanese yen, for example. So this then just a summary of the main currencies in comparison with the rand in this particular way. Let us also consider the exchange rate in the reverse order. In other words, comparing the rand value to other currencies. So the value of 1 rand is a good measure of doing this. So in the table below, table B, we will consider the value of 1 rand compared to the other currencies as we saw before. You can also consult your newspapers for the latest exchange rate, since this particular ratio changes all the time amongst the different currencies. So in this table we would like to see how many pounds, for example, can 1 rand buy. So 1 rand in this case buys 0.07593 British pounds. So clearly it is the same expression as before. One can see that the rand is weaker, since we don't even get 1 British pound, much less than 1 for 1 rand in exchange. And the same with the euro. 1 rand will buy us 0.09426 euros, and in the case of the American dollar, 1 rand will buy us 0.11968 US dollars. So in the first 3 cases then, it is exactly equivalent to what we had on the previous slide. It is just the ratio expressed in reverse order, or the reciprocal of the ratio that we have had before. For example, if you take 1 divided by 0.07593, you will get exactly the ratio that we had before on the previous slide, 12 point something, and so on for the euro and for the US dollar, as well as for the yen. Note that in this case, 1 rand will buy us 9.29368 yen. Again, this table is an expression of the fact that the first 3 currencies are stronger than the rand, and finally the Japanese yen in this case is a weaker currency, since 1 rand will buy more than 1 Japanese yen. We will now consider a number of examples of currency conversions. Consider the following exchange rate extracts from a daily newspaper. We have the ratios as indicated on the screen between the British pound and the rand as indicated, Japanese yen and the rand as indicated, and then there's also an expression of 1 rand in terms of the euro and 1 rand in terms of the US dollar as indicated on the screen. The question here is, use this particular exchange rate expressions to exchange 100 rand to pounds in the first instance, secondly 100 rand to yen, thirdly 100 rand to euro, and fourthly 100 rand to dollar. So let's see how this is done. In the first instance, 100 rand in this case will be, in terms of the British pound, 7.5929 pounds. How do I get this? I have to divide by this exchange ratio or exchange rate given in this case. So whenever the foreign currency is expressed in terms of rands, if I have rands and I want to convert it back in terms of the foreign currency, in this case the pound, I have to divide by that particular ratio or the value, in this case 13.1702. In the second instance, 100 yen or 100 rand must be exchanged to yen rather. So in this case again, I have the yen, 1 yen in terms of rand, so I have to divide by this ratio in order to express rands in terms of yen. If I have 100 of them, clearly I just divide by 0.1076 in this case, and I have the answer that 100 rand is equivalent to 929.368 yen. In the third case, to express 100 rand in euros, I'm given this particular ratio. I have the rand in terms of euros in this case. So here I have to multiply. If I have to express now 100 rands, it's 100 times what I have here. So it's just that particular ratio multiplied by the number of rands, in this case 100. So there we go. Just shift the decimal point 2 places, and I have, this is equivalent to 9.426 euro in this case. That's 100 rand. And in the fourth instance, again, I have the ratio of 1 rand in terms of the American dollar with this particular ratio. So 100 rand clearly will just be 100 times this particular ratio, and this gives me the dollar value of 100 rand, in this case, namely 11.968 US dollars. So hopefully this will be clear how to convert one currency into another, particularly if you have a number of rands and you want to convert it to either the pound or the yen or the euro or the dollar. This is the way to do it. Just be careful and have a good look at how the ratio is expressed, either the foreign currency in terms of rands or 1 rand in terms of the foreign currency, and that must be considered in order to exchange the value of your rands in this particular type of example. One instance where exchange rates become very important is where I would like to buy a specific item, and I know I can find it in various countries, and I would like to compare the price of this item expressed in the different currencies, and I want to exchange it to rand in order to see where I can get the best buy. Here we have an example of such a case. James, a keen golfer, wants to buy a Tiger Woods putter. He discovered on the internet that he can purchase this putter in Hong Kong, that's Japan, for 21,375 yen. And he can buy the same putter for $287 in New York, in the United States of America. Question: which of these buys will be the better one? Given in this particular case, we have the exchange rates as we've seen before between the pound and the rand, as indicated between the Japanese yen and the rand, and we also have 1 rand expressed in terms of the euro, 1 rand also expressed in terms of the American dollar as an exchange rate. So how can this help me to solve this problem? If he considers the exchange rates above, which offer is the best, the Japanese offer or the American offer? Now, if I have the cost of this particular putter as 21,375 yen, to exchange this into rands, clearly I just have to multiply by the ratio given here, because if 1 yen costs so many rands, then 21,375 yen will be this particular number times this ratio, which gives us then an amount of 2,299 rand and 95 cents. I have to do a similar exercise to exchange the cost of the putter in American dollar, 2 rands, and then compare the 2 rand values of these items in order to see which is the best offer in this case. So 287 American dollars. I have the exchange rate 1 rand in terms of dollars, and I would like to exchange dollar to rands. So whenever it is in the reverse order like this, I have to divide by this ratio, as we have seen before. So we divide by the ratio in such a case to change the dollar value to the rand value. And if you do that, use your calculator, you see that the cost in America of the same putter will be 2,398 rand and 6 cents. So clearly, the Hong Kong offer is the best, as it is about 100 rand cheaper than the offer from America. We will now present the 6th and final tutorial of this video, where we will consider a problem on exchange rates. Let us study the following exchange rate table. We are given here 2 countries, the United Kingdom and the United States, as well as the corresponding currencies, the pound and dollar, as indicated on the screen. And in the 3rd column we have the exchange rates in rand terms for these 2 currencies. The following problem then. Ashwin and Cosmo are waiters in a South African restaurant which attracts many tourists from abroad. Ashwin receives a tip of £6 from a tourist, and Cosmo similarly also receives a tip of $12. The question is, who received the better tip? At this point in time, I suggest that you pause the video, do tutorial 6, and come back and have a look at the suggested solution. Let's have a look at the solution for the problem in tutorial 6. Now, from this problem, we need to compare the rand values of the tips that were received by the 2 waiters, Ashwin and Cosmo. In this case, Ashwin received £6, which, if we express it in rand terms, must be multiplied by 14.13, that is the exchange rate, as we have seen before. So Ashwin received a total of 84 rand and 78 cents. If you look at the tip that was received by Cosmo, he received $12, and we know the exchange rate in rand terms is given in the table as 7 rand and 4 cents for each dollar. So we have to multiply that with the $12, and in this case we see that Cosmo received 84 rand and 48 cents. Clearly, Ashwin received 30 cents more than Cosmo in this particular case. We have come to the end of this video on financial mathematics. Remember, consult textbooks for additional examples. Attempt as many as possible other similar examples on your own. Compare your methods with those that were discussed in this video. Repeat this procedure until you are confident. Do not forget, practice makes perfect. Goodbye and good luck.